Okay, well, I wanted to welcome everybody to our first on-campus STEM lecture series event of the fall 2022 semester. So I'm really glad everybody's here tonight. I'm Don Barry. I'm a professor of geology, and I help coordinate the STEM lecture series. So a couple of quick announcements. If you're here for extra credit, which I imagine probably a couple of you are, we have a sign-in sheet, so feel free to print your name and the class and your professor, and I'll make sure that your professor gets that information, as proof that you were here tonight. And I also just want to mention that we have some really good events coming up a little bit later on the semester. So check social media, and we'll keep you informed on that. We've got a talk coming up about the physics of helicopters, how helicopters fly. That should be really interesting. And then a little bit later, I think in December, we have a talk by one of our biologists, Dean, who's going to talk about, I think it has something to do with dinosaurs, as I recall. So we'd love to have you for that. But we're here tonight to hear an illustrious speaker, Dr. Pat Abbott. And I want to tell you a little bit about Dr. Abbott. I just heard him say he's been teaching and giving public science talks for going on 40 years now. And, we're hearing a lot these days about natural disasters. That's a big topic in the news. Dr. Abbott literally wrote the book on natural disasters. And for a long time, the course in that same topic that he taught as a professor at San Diego State University was the most popular course that San Diego State offered. So, and then since retiring from San Diego State, Dr. Abbott has lectured and taught and led field trips all over the world, including places like Patagonia, Antarctica, New Zealand, Iceland, and plenty of other places. As well as he's also very popular for local news stations. Very often when there's an earthquake in San Diego, I've seen the news stations line up one after another to get the opportunity to talk to Dr. Abbott about earthquakes. So it gives me great pleasure to introduce Dr. Pat Abbott, our main speaker tonight. Please give him a warm welcome.
Thank you, Don. Well, I'm glad post-pandemic, or we can even say post-pandemic, this is my first time in front of an auditorium since, what would it be, February of 2020. So it's a pleasure to be out, and I'm glad you all are here. So what I want to do tonight, of course, you've seen the title of the talk, and I guess as a geologist, maybe I should say this. Everybody knows the word mesa in Espanol means table, but since the 1800s, a flat-topped hill that's wider than it is tall, geologically speaking, is called a mesa. It's an official geology term. That's not the main point of the talk today, but just thought I'd mention that. And they just called me back to San Diego State to give me this pointer. This was used when it was called San Diego Normal School over 100 years ago, and I'd never used it before. I thought it's kind of trippy to go back a century and use this as a pointer. But I also have this, if this isn't clear. Anyway, let's get started here. So we hear so much about climate change and all these sorts of things going on. I thought it might be just kind of fun to project some of this forward through this century. So for many of you who are going to be around for this entire century, let's take some kind of look at the future to whatever extent we can. In California, the four seasons, we're a little bit different than other places. For us, it's flood, drought, wildfire, and earthquake. And I thought we'd project or look forward through the 20th century and maybe get some kind of an idea of what we might be experiencing. So, the bottom line of all of these things starts from the fact that the Earth is heating up, it's warming up. Now I have here, this is one from NASA. You have almost identical curves from the National Weather Service, from the Hadley Climate Center in Southampton, England, and from the Tokyo Meteorological Society. So that my point simply being, if I put all four of them up, it just looks like a braid. The good news is scientifically you get the same results in different parts of the world. In other words, this is not really anything that's debated. So here's 1880, and of course each black square here would be the temperature of that year. And what do we see here? We see weather varies all the time, but when we smooth it out, as they've done here with this red line, this is what we call climate. that saying goes, you know, a climate is what you expect, weather is what you get. There's no real obvious pattern to each black square, but you certainly see the warming. And I only have this through to 2020, so if we keep it going again, the last couple of years have extended the heat. So without question, the Earth's atmosphere and ocean are heating up very, very rapidly, and it's making changes. And one of the things I just wanted to mention here at first, this is the famous Keeling curve from Charles Keeling, formerly out here at Scripps Institute of Oceanography, looking at CO2. The tooth pattern there is the fact that carbon dioxide varies from spring to summer, depending on how it's going through life. But the overall pattern, you see, when he started this in 1958, there was 313 parts per million in the atmosphere. And now, I haven't put the most updated one here, we're now up past 420. So there's a warming thing. And oddly enough, people have said it's not even proven that carbon dioxide, the greenhouse effect, actually makes things warmer, which just amazes me, because actually that was published and made clear in the 1850s, and it's been something that's been known for a long time. Now, I mentioned that one showing the heat rising on the first diagram, and then the CO2 here. Not that that's news to you, but the thing that's very, very fascinating to me is taking three simple quantities here. The Japanese mathematician, you see here's a bunch of words for you, but we've got the 2021 Nobel Prize in Physics, and here's what he did. He took the CO2 we're just looking at, the temperature rise you're looking at, and the amount of water vapor in the air, and taking those three things, he did computer models. And the trick of doing computer models of the weather is every little change you make it a degree hotter and other things change. Add a little more carbon dioxide, so it's one of those kinds of things you make a little change and then dozens or hundreds of other changes go. And it was so complex, nobody's been able to figure it out. Well, what he did here is he figured that out. And here's one specific thing he did in 1969, 1970. He, using those three things only, CO2, water vapor, and this solar radiation, the heat, he predicted the temperature in the year 2000, 30 years later, and only missed it by 1 degree Fahrenheit. So for all of us, all along you say, well, it's a computer model, how close is that to truth? This is so stunning. And he didn't get the Nobel Prize for predicting the temperature, but for being able to take these highly variable changing factors and make sense out of them. So I mentioned that to show even more that we actually know a lot about what's going on in the atmosphere. So the heating atmosphere, what we're looking at tonight, are drought from the heat in the atmosphere, the vegetation drying out for wildfires, and the ocean water not at heat it holds. It's actually stunning. They have pretty good numbers on it that show that about 90% of the excess heat that humanity has generated has been absorbed into the oceans. In other words, we're not even really feeling the main effects of all we've done because it's going into the water. And think about it, the surface of the Earth, when you look at it, they call it Earth, but some have said it ought to be called planet water. But what, 71% of the surface of the Earth is water. And every place the atmosphere is in contact with the water, heat and CO2 are being absorbed into the water. So the oceans are saving us from a lot of what we've been doing. Now, here's one of the main points. And a lot of these things I realize they've been said a lot in the news, and it's not the first time you hear them, but I'm trying to make a coherent thread we follow here. And one of the things is it's not that you're necessarily seeing a lot of things you've never ever seen before, a big flood, a big wildfire, or things of that sort, but they're more frequent. And this, to me, is a beautiful one for showing that. So here's the United States billion-dollar weather disasters. The different colors, I don't know, it's probably too fine to read from where you are, but it's different kinds of weather disasters: hurricanes, floods, wildfires, different colors for them. And this, I might add here, CPI means this is all adjusted to all dollars are the same. So we're looking at a change in the number of billion-dollar weather events. So here we are in 1980, look how few they are. 1987, you don't have one. Then we go over here and you have 16 in the years, what are all those things? 2011, 2017, 2020. So I mean, when you look at that, you say, clearly, we are seeing the extreme events, the things they talk about, and some say, no, it's the same old thing. No? Well, yes, a lot of it may be the same old thing, but the no part is the frequency is hugely going up. And I might also add that this one here I just put into the latest edition of my textbook that is already out of date because 2021 doesn't have this. And in 2020, well, a little something didn't come through. What I wanted to show was here, in 2021, we had $20 billion events last year. So in other words, this curve here has to be pushed up even farther. The things are coming faster. The extreme events are coming more faster than ever. Okay, so now let's go after our specific seasons here. Floods we'll call season 1. It takes water to make all these other things work. And are you familiar with atmospheric rivers? They're in the news quite a bit now, and they're very significant events. And the first thing I'd like to call your attention to here is this diagram from the Center for Western Weather and Water Extremes. That's out here at Scripps Institute of Oceanography, and they are world leaders in the study of atmospheric rivers. So I want to give them full credit. But what we're seeing here with these colors, we're seeing water vapor in the air. When I say it's river, it is a river. The amount of water in here held in atmosphere. So this is over 1,000 miles long. It's like 600 miles across. It's about 2 miles thick of water vapor. And the volume of water in here is about the same as 25 Mississippi rivers. So what are we looking at here then? When these atmospheric rivers come up, if they hit a place in the land, air goes up over the mountains, the water solidifies and liquefies and falls. These are huge weather-making events, rainfall events. And part of what we're talking about here is the warmer the oceans get, the more moist water goes into the air. Atmospheric rivers are on all oceans. I'm just showing the Pacific Ocean here, just since here we are in San Diego. I'm just showing one for us. But they're in all ocean basins around the world. And this means, or presumably as we go through the century with more heat, more water vapor in the air, more atmospheric rivers, more huge floods. We're going to look at really the huge floods here a little bit. So here's a picture again. Here's San Diego here, Baja California, Pacific Ocean. This is what we hear a lot about. Here's one of the atmospheric rivers, photographed. That's the one they call the Pineapple Express for us. So what's happening globally? We've got that hot water down around Hawaii. What's Mother Nature doing? Exporting that heat and that moisture and moving it up to colder latitudes. Now, it turns out California's biggest flood was very early in our recorded history here, 1862. This particular flood, they had like 43 days of almost continuous rain. Atmospheric river after atmospheric river hit different places, primarily Northern California. And they reconstructed this here. The U.S. Geological Survey did, taking the 1862 rains and then put it on today's map. So the dark blue here is water depths up to 20 feet. So look here, look at the Great Valley with Sacramento in it. Look at the whole agricultural Great Valley here. You basically turned California into a land of lakes. And the reason I mention this right now is, that's 1862. Like I say, on the one hand, we've always had extreme events, but as I mentioned, as oceans heat up more, as atmospheric rivers are loaded with more moisture, we're liable to see more events. And well, sort of like this. If it did happen, it can happen again, and then not only maybe more frequently. So for us, atmospheric rivers touching San Diego, I throw in a couple here. Otay River Valley. So here you see the remains of the dam. We were hit by two successive atmospheric rivers in January of 1916. And the failure of the lower Otay Dam there set a wall of water 40 feet high down the valley, and that still stands as the 6th deadliest dam failure in U.S. history. And then one other shot of that from that same atmospheric rivers, you see here the date here, January 28, 1960. here you are looking over at Old Town. Water was flowing from bank to bank through Mission Valley. So I'm going to history here a little bit because we're expecting history to be repeating itself more frequently as we go into the 21st century. There's one other thing I want to do with floods, hurricanes, and perfect timing, because what we just have last month, we got Tropical Storm K coming up here, which was stunning to a lot of people. But first, let's talk about hurricanes in general, and then bring it here to California. So here's North America, and I think for us, we think of hurricanes primarily the ones that come across the Atlantic Ocean from Africa and come up and impact us. And then there's a lot of the ones that form here in the Caribbean Sea and come up to the north and impact us. And to us, those are hurricanes. And, I mean, they are. But we don't really get them on the west coast. But if you look at the coastline here, here comes Mexico down here. And the sea, the shoreline starts going in through Central America and down. So there's a very warm water area here called the East Pacific Warm Pool. And as you can see, a lot of these hurricanes generate here. By the way, the color of them, whether it's category 1, 2, 3, 4, 5, the red, pink colors are the most intense. So most of those move on west out of the ocean, but as you can see, some of them go north. So what stops them from coming up and getting us?
Water's too cold.
Water's too cold, exactly. Because what is the energy in a hurricane? It's the heat stored in the upper ocean, the upper 200 feet of the ocean. The number we usually use is 80 degrees. We want the water temperature to be at least 80 degrees Fahrenheit. The hotter the better. And then the winds carry that moisture up, and that's the heat in the hurricane. But when you go up over cold water, now the hurricane's hotter than the water, so the heat flows out of the hurricane into the water and it dies down. So that's what you see, these things dying down. And then last month, September the 9th, the remains of Tropical Storm, Tropical Storm K, when it hit us, remains of Hurricane K. We got, what, 3/4 of an inch here in San Diego in September. So as this water mass here gets warmer and warmer and warmer, then it's only reasonable to expect that more of these will make their way northward. And I think events like Tropical Storm K, which actually did a lot more good than it did harm, actually, but I mean, should be seeing a lot more of those kinds of tropical storms coming up here. And with the hurricanes, there's three big factors. You know, one is the wind speed. That's what they usually talk about. We'll be getting the tropical storms, so the wind speed's not the worst. The deadliest has always been the storm surge. We've just seen that with Hurricane Ian over Florida, where water up to 18 feet high came on land and killed lots of people. But the third factor is the flooding, the rainfalls. And when you think about a hurricane, forget about the wind, forget about all that. It's holding all this water up in the air. And as it loses energy and weakens, it's going to drop all that water it's carrying. So a tropical storm could still do loads and loads of flooding. And I have the statistics for this. I didn't put it in here because we're focused on down California. But classically, hurricanes are things that hit the coastline and do the damage. What are we seeing in recent years now? What we're seeing is they don't just hit the coastline anymore. They're carrying more moisture than they did. And they're carrying severe flooding, tens of miles, 200 miles inland, where you have big floods that are causing tremendous damages. So the tropical storms are going to be able to, or are doing, more damage farther inland than they used to. But one other little, well, I'm just taking a closer look on this. So these are all actual tracks. This is an artwork. A number of them cross over, get a little more energy out of the Gulf of California and go into Arizona and New Mexico. But here's us. The only tropical storm made landfall on California was 1939 here in Long Beach, but that killed 93 people. Tropical Storm Kathleen hit on the backside of the mountains on September 9th again, same month and day, and that killed 10 people, mainly water flowing this way. But San Diego hurricane, I didn't draw this. This is actually drawn wrong. The red line, it doesn't go. Oops, that's a change of topic on that. In the meantime, what I wanted to do was Okay, I can try to use, I'm going back a century. So take this red line, and instead of doing this, do like what Kay did. Bring it up like this and bring it out that way. See, a lot of the thought people, they associate like making landfall as the big deal of a hurricane. No, it covers a huge, huge area. You don't have to be hit by this. The winds on the fringe of it bring in plenty of water to storm itself. And that's what happened in 1858. It literally was a hurricane, 81-mile-an-hour rotating winds, but it went like that. Anyway, we expect more of those. Well, you already had a preview of the next topic. Then we're going to dry it out now. Season 2. So here are these drought maps. This one you can see is from 2 months ago. And when you look at, here's a measure over here. It'll be bigger on the next diagram. But droughts in the southwestern United States, that's nothing new. So again, we're talking about increases in frequency and duration. Now here we are just focusing on California. This was last week. So exceptional drought, you see that? You see we are getting off pretty easy right now. We're just in moderate drought. But this is nothing new for us. But the more we get of these, more frequently we get them, and the longer they last, well, obviously that hits the very fabric of civilization. Here's another diagram about droughts. Here's the year 2000 to 2020, and we're looking at area covered. Here's 100% of California being covered or none. And when you look at the droughts now in terms of area covered, you see the droughts make the news, and they say, oh, this is the biggest drought ever, or this and that kind of thing. I'm more concerned with, or think more relevant, just thinking about the fact that droughts are a fact of life in the southwestern U.S. They have been for thousands of years. They still are. They're probably going to get longer, be more severe, but it's nothing new in that sense. It's more numbers of them, more extreme, longer duration. Now, I wanted to focus a little bit on heat domes, so I thought first I'd just go back to high atmospheric pressure. That high they put in the weather maps all the time means the air is flowing down and out and then into a circular pattern on the ground. But that descending air warms as it comes down. What I want to talk about now are heat domes. We've been experiencing some of these lately. Now, on the one hand, a heat dome is just a high pressure, like we just did in the last diagram. But if we look at this one we're going to talk about that occurred a couple of years ago, you can have hot air here, say the bottom of a few thousand feet, and then have a high pressure zone come in on top of that. And to make a dome that if it's trapping hot air underneath it, and it itself is going to get warmer as the air circulates here and drops down to the ground, then we're going to trap tremendous amounts of heat. We're going to look at one in a little bit, but I want to set this up. So there's the heat dome. On the one hand, it's just a regular atmospheric high pressure zone. On the other hand, we have more hot air to trap beneath them, and some of them are coming in hotter. And another fact, here's another significant point that comes up in a lot of different topics. And that is to say that as the Arctic warms, and I have a map coming up to show some of this, we use this term Arctic amplification. The Arctic is heating up faster than any other part of the world. Well, as the Arctic gets warmer, the equator stays hot, the lesser the temperature gradient. Let's put it this way. The colder it's hot at the equator, keep it hot. If it's cold at the Arctic, then the winds go around the Earth fast. The warmer this gets, and you decrease the gradient or the difference, then the slower the winds go. This is significant. This means things like a heat dome that might have sat over some area of the U.S. for a day or two, now could be there 3, 4, or 5 days. So if you're doing the damage, you're doing it a lot longer. And affecting agriculture. I'm going to wind off a little bit here. Well, you can read this. Drought, famine, migration. Actually, one of the things that I think is most significant, we're just going to take a little look at here, of what's going to happen as the world warms more. We're going to see more crop failures. We're going to see more people in trouble. And trouble, I mean making a living, trouble. And that means what? Through history, that means more migrations. And so what we're going to see is greater migrations of people. Now here, I want to look at global population. To me, well, Don said I've been teaching 40 years giving lectures. Actually, I was 40 years on the faculty of San Diego State. I know I look like a young kid to you, but I've actually been doing lectures like this for 60 years. I'm in my 80s. So, but for all that whole time here, I've considered the biggest problem on Earth the exploding population of humans. And I want to look at it here a little bit. In the year 1800, after 200,000 years, we got up to 1 billion people on Earth. And I'm not talking about countries, or I'm not labeling other than human beings. That's all the farther I'm going on any label, humans. In 1922, we got up to 2 billion. 1959, 3 billion. And then look at the difference. Each of these years here is adding 1 billion people. So when you look at this, and these are my numbers, my diagram. I'm more aggressive than the U.S. Census Bureau or the United Nations. I'm going to be rude. They're cowards. Nobody wants to face up to the problem of population, so they try to avoid it. All I've done here is just this. 13 years difference, 12, 12. I just extended it and made it 13, 13, 13. They might be 12s. And see, I get to 10 billion people by 2050. Nobody else does that. I'm just trying to say it's a problem that needs to be addressed in some form. Okay, so here's this. Look at this. So in my lifetime, the world population has tripled. Now, here's California. That big flood we had in California, 1862, look, hardly anybody lives here. There's only about 400,000 people in California. And so the measure of the flood, if I said it killed 4,000 people, that doesn't sound like much these days. On the other hand, 4,000 people, that's 1% of the people in California at that time. And of course, what California's done is, that the blue, this isn't my diagram, the other one was. The blue, they're here, we're up to today, then they're just projecting it on farther. I don't think anybody's going to suggest that California population is going to go down. It's going to go up. And I'm not judging anything here or labeling anything here. We're just trying to look at changes. What are trends? What's going on here? And we're going to be seeing more and more people coming in here and migrating globally. So here's a NASA diagram for computer model for the last decade of the century. And you notice up here the extreme increases in temperature. This is centigrade, so you can almost double these. And so that means up in areas up here, you're going to be talking about the annual temperature being like 13, 14 degrees higher than it used to be. So goodbye glaciers, goodbye ice on covering the Arctic Ocean sorts of things. For us, if we stay right here, you see those colors, we're right in this area in here, so which means temperature, average annual temperatures here would be 7 degrees or so. Instead of this being 70s, it would be 80s. Instead of summer highs getting a little bit over 100, they'd be 100, 110. And you can take it, but you know what can't take it? Agriculture. The food that supplies all this number of people, which is growing larger all the time. So this is going to be one of the biggest things for people to deal with in this 21st century. It brings up a question, which I just put it here, is what is the carrying capacity of the Earth? If we forgot all the politics and all those things and just looked at it as, here's this planet, here's water, here's land, here's crops, what would be the most appropriate or best number of people on Earth? I don't have an answer. I'm just saying that I think it's a very significant question to think about what would be the best way to inhabit the Earth. Okay, wildfires. Season 3 now. A lot more change than just spring, summer, fall. So this is San Diego. This is a 2007 fire in San Diego, the Harris Fire, just for the heck of it. So what I've done here is I took California's 21 largest wildfires. They started keeping records here in 1932. So if you see here in this 91 years here, you see there's 3 of them. And this is the 21st biggest one. I forced that onto the top, added to the top 20 list because it was a San Diego one. And then our Cedar Fire in 2003 at that time was the biggest fire in California history. Now it has 10th place. So here's these. It's probably more effective if we go to this graph. So here's a little histogram. Here's numbers per decade. So 1930 to 41. You see no big wildfires, no big wildfires. Here's 2000 to 2009. We had, 4 of them. 2010 to 2019, this many. And then you see this, but this one here, we haven't done that decade. That's just 2020 and 2021. So if we try to project forward, here's what we have seen. So we still have 8 years to go in this decade, so that number's going to go up again greatly. So if we look at wildfires, and this is what I'm talking about here is size of fires. We now have terms we call mega fires if they burn more than 100,000 acres, and we call them gigafires if they burn more than 1 million acres. We've only had 1 gigafire so far, but every one of these is a mega fire. So what are we seeing? The truly large wildfires. Isn't that just screaming at you? Are they changing in time? Are more extreme events coming? I'm not talking politics or opinions here. I'm just simply plotting data. You can go on CAL FIRE and look at, they have tables about the size of the fires they fought. All I've done is taken that data and made a visual out of it here. Now, I'm going to back up a second and set up the next thing. Now we've looked a little bit here at floods, droughts, and we're into wildfires now. But how about if we take a recent hurricane and a recent heat dome and put them together? What happens? And what I want to do here is look at an event from 2 years ago. You may remember this. So here we are, again, here we are in San Diego, here's California. But here's this high pressure zone, a heat dome, and this is one that's hung around for several days. And so remember I said the diagram I was showing, I said you can have hot air here at the ground and then have another high pressure come in and make a dome or a cap on it. Well, we had temperatures down here like at Death Valley, they were going close to world record, 130 degrees Fahrenheit. Now run a heat dome over that, have that air descend and warm as it goes towards the ground. So here's an intense heat wave. Now, here's Fausto. You could think of Tropical Storm K we did last month. Here comes the exact same thing. Hurricane Fausto. And what we're seeing here is the relic leftover moisture from Fausto coming in and intruding into the heat dome. So now what happens? Here's the heat dome up here. Here comes all that moisture in there. That moisture added to a lot of other heat, thunderstorms. So you're feeding this in, making lightning bolts, and they instrumentally can count lightning bolts now. So in the 3-day period, almost 11,000 lightning bolts hit the ground. And it's what we call dry lightning. And dry lightning means the rain doesn't hit the ground. The temperatures here in the hundreds. So when the moisture comes into the clouds, the rain is falling and it's evaporated into the air and doesn't hit the ground. So that means the lightning bolts could start their fires. And that was a raging set of fires we had at that particular time. Now I put these two things together because this could be K coming into a heat dome. Notice I'm not talking about things that are totally fanciful. This is 2 years ago, California. And this combination is something that they don't have to always be as bad as this one, but this is a combination of things that I think is reasonable to expect to see once in a while. So the fires from this one on that top 21 list, the biggest fire in California history, 4th, 6th, and 7th. 4 of the top 7 came from that particular collision of tropical storm and heat dome there. And again, I'm looking at these things, in a sense, it's just an example, but I'm looking at them as things that I think are going to be replicated more often, that we're glimpsing events that are going to become more familiar to us. Now, remember the town of Paradise in this fire? Here's the fire photo. I love this photo. Actually, it's the cover photo of the 12th edition of my textbook. I didn't take it, but here's the fire. Here's the wind blowing it. Here's the town of Paradise. So steep, mountainous terrain, windy roads. You got to get out away from this fire coming in. Now I've got, the next thing is just a bunch of words. I'm sorry, but I have a point I'm trying to make out of all of this. Bad business in my view of putting a lot of words on a slide, but what I'm trying to do is give you a basic idea of something here. Fire lasted for 7 to 18 days. Firefighters, and I give them all praise, but the fire's too big for them to put out. It took rain to stop it. You see the number of buildings destroyed. 88 people died in their homes or cars, homes that didn't get out, or in their cars tried to escape. What I'm after is not just that fire. The next thing is what I'm really trying to set up. This isn't the first time. Humboldt fire, 10 years earlier. Read it. And so what did they do after they had, they only had 2 deaths that time, but after that they decided people dying in cars because they can't get out, we've got to do something. So the grand jury says, let's build a 4-lane road going through town, for example, picking one example. What do you do to make it easier for people to escape if another fire comes? 4-lane road. Then the residents are complaining, people are driving too fast through town now with this big road. Let's reduce it back to a 2-lane road again, which they did, and then some of those same residents died on that 2-lane road because they couldn't get out. So what am I after right here? I'm trying to say, what part is Mother Nature and what part is humans just plain making mistakes? You have to learn. I'm not trying to be a purveyor of doom or, things here, but I'm trying to say, we have to understand nature to live with nature. You can't defy it. So one other photo from this I think is very stunning. This is campfire also. You notice that here's the green pine trees of the forest all around. And then right in the center of the forest, here's this subdivision of homes. And it looks like 90% of them have burned to the ground. Does that make sense? The forest fire, the forest didn't burn. It's part of that same fire we're just looking at the image of. So how come all of these burn and the trees don't? Well, one, that's those flying embers. You see those pieces of orange burning material flying through the air? Well, what's that tell you? That when all these embers are flying through here, the houses, and I'm not just picking on Paradise, I can do the same thing for San Diego. The houses are more of a fuel than the pine trees. They build the houses wrong. That's not Mother Nature's fault. This is bad buildings. This is people not recognizing the environment you live in. Did you have a question?
Oh no, I was just going to say, because I'm from Lake Tahoe, so when we have to evacuate for fires, there's instructions to push all of your furniture and everything to the center of the house so that it lessens the chance for it to go up and catch the house on fire. I don't know why, but I just thought it was awesome.
That's interesting. Seriously describing there that the South Lake Tahoe fire, that was a little high on that 20 fire list that or 21 fire list that we just had. She was saying they were instructed to take all the furniture and move it into the center of the house. I mean, because the furniture is what, fuel? So they're trying to get it farther away from the walls. What I usually hear about that, and this may be the step before that, is the heat can come up to the house, and even if you have the double or triple pane glass, you might radiate enough heat through that the curtains catch on fire.
Yeah, exactly that too. You have to rip all the curtains off the walls.
Okay, because then the curtains could then be the things that would start the furniture from burning. So yeah, so get.
So that kind of fabric will just go up in flames with any sort of heat.
It makes a lot of sense to me. You're trying to remove fuel away from where the fire could get to it.
And like the furthest place from where the heat will come in. So like that.
Right. And did it work?
Yes, my
Good. Good. Okay, so we need to do a lot of rethinking about this. It's kind of paradoxical to me, because like Don mentioned at the beginning, the main thing that people like to ask me questions about are earthquakes. And I think that's because earthquakes are kind of mysterious. That's not part of day-to-day life. And people will listen more because they're going to learn something you don't know much about it. The fire is so familiar. Oh, did I put that up here? Oh, I did. Fire is so familiar that I don't think people, they don't fear it. They think we control fire. No. Not always. Sometimes. Wildfires are doing more damage than earthquakes in California here in the last several decades. Okay. The fourth season, I call it the unpredictable season. I'm going to say it twice, so here's the first time. We have no ability to predict earthquakes. Or put it another way, if somebody says they can predict earthquakes, don't believe anything they say. We don't know how. But there's a lot we can say, even though we can't do that prediction. So here's a map of western U.S. So here's the tip of the Baja California Peninsula. Here's San Diego. Here's San Francisco. And you see these numbers on here? These are, have you done plate tectonics? You know, C4 spreading, transform faults. If you haven't, I'm not going to go do that. But if you took Don Barry's class, you'd know all this stuff without me even saying anything more. But my point is that these numbers are in centimeters. That's how much the surface moves in a year. So in other words, we understand things well enough. We know what the movements are. And this map here is over 50 years old. So I'm not talking about brand new stuff here. My point simply being that if we look at California now, we can take our biggest fault here. This is the San Andreas fault. I'm doing it piece by piece. So here's the movement in 1857, the Fort Tejon earthquake. When you go over Tejon Pass, driving up towards the Great Valley. So here, the ground ruptured along 225 miles with the maximum movement, horizontal movement of the land, 31 feet. My favorite one is a circular corral for animals. It was opposite. So it's kind of cool. Well, things that amuse me anyway. So in 1906, the famous San Francisco earthquake, here in a 250-mile length, the ground moved as much as 20 feet. And then if we look at the third segment of the fault, the one down by us, here we are, that hasn't moved since around the year 1690. Now, this is not history. I'm going to come back to this. This is not science. It's history. If you're going to look at that and you say, which segment of the fault, it's one continuous fault, which segment do you think would move next? I think I'd pick this one. But would Mother Nature pick there? Could this one move and this one both move again before this one? The answer is, I know the answer to that. The answer is yes. When I say we can't predict, we can't even predict something that looks as obvious as that. Okay. Now, I want to set up, well, what I'm building up to here a little bit, I'm going to give you I can't predict earthquakes, but I'm going to give you 4 big earthquakes that are reasonable to expect to happen in California this century. So what I'm working on now is, here's the tip of Baja California Peninsula, Cabo San Lucas area, was back here, part of the state of Nayarit, and it's been pulled apart like 300 miles. And then here is San Diego area, pulled away in today's political terms from the state of Sonora, Mexico. So this whole piece here, in your mind, slide it back against mainland Mexico. That amount of movement has taken 6 million years to do. So if that's been moving for 6 million years, and you saw the numbers on that other map, this area 8 centimeters a year, another area 6 centimeters a year. If it's been doing that for 6 million years, does California have earthquakes coming up in their near future? Obvious yes. You can't say the month or the day, but we know they're coming. So I want to look at some of these faults here then. So here's the Salton Sea again. Here's San Diego. Here's Los Angeles. And we're going up Santa Barbara and on up the coast. So here's the San Andreas Fault. Here's the San Jacinto Fault, and you notice the San Jacinto Fault merges with the San Andreas Fault. Then the city of San Bernardino. If you like you want to be near a really big shake, I would recommend move to San Bernardino. So here's the Elsinore Fault running through here, and then here's our Rose Canyon Fault. So we see each of these faults has the same pattern. The left side is moving this way, this way, this way. You can almost visualize it like a deck of playing cards, you know, where you're pushing them all at the same time and they're slipping aside each other. Just one little look at San Diego. So the main faults come through here. North Island and Coronado Island used to be separate. The faults had a bay right through there. They filled up the bay, buried the fault. So here's the big fault zones coming through San Diego. These could be part of our latest published thing on that is, and this is a consensus number, could be an earthquake as big as a 6.9. Could be. Doesn't have to be, but could be. Okay, now, 4 big earthquakes for the 21st century. All right, here they are, and I'm going to go do a picture for each one of them. So the first one here, I'm going to go to, again, here's San Diego, here's Los Angeles, here's Salton Sea. So this is that segment of the San Andreas that we had when's the last time it moved, around the year 1690. So we're making that number 1 on the list. Not off of science, but off of the history. It's been a long time, ought to do something. So these are decided on by what we call working groups, seismologists, earthquakes, Darn near anybody who wants to be a part of it, part of the work can. So it's the best assessment, collective assessment we can get on these things. So the idea here is that this would be a magnitude, if this ruptured the 185 miles, that would be a magnitude 7.8 earthquake. Obviously a big one. Let me bring up another point to you. They arbitrarily picked and said, well, if it starts rupturing here at the south and goes up to the north, visualize San Bernardino. Try it the other way. How about if it started up here and went that way? Would San Bernardino get the same effect? No. If you're in San Bernardino and this is moving up from the south, up like this to you, the energy is being forced your way. If you're at this end here and it's starting here and going away from you, you're not getting hit as hard. So I'm just saying, we don't know how it's going to go. The 1857 segment that moved here, that moved from north to south. The Loma Prieta earthquake in San Francisco in 1989 split in the middle and ruptured north and south simultaneously. So we don't know how it will rupture. But that's a biggie, and we would definitely feel that here. The next one, I'm going up to the Bay Area, and we're picking on here the Hayward Fault. Here's San Francisco Bay, city of San Francisco, Golden Gate Bridge here. So we're coming up here from east of San Jose up through Hayward, Oakland, Berkeley, Richmond, that area. There's assessed at 27% chance that would move between 2013 and 2032. This has been redone, and there's a new one, updated this now, from 2014 to 2043, it has a 33% chance of moving there. If you're familiar with driving up the east side of the Bay, what is it? It's one little old town after another, densely packed. That's going to be a brutal one. They projections of how many people might die, they count that in the thousands. You know, one of the biggest factors, time of day. When would you, if you could pick, what time of day would you most like to have the earthquake? For most Californians, it's when you're home, asleep, in bed. And the other buildings and structures you're out on are actually more dangerous. So the projected death toll is almost a factor of 4. 4 times as many die if it's at 3 p.m. as that rather than 3 a.m. Again, not that you have control over it, but being at home in bed is a great place to be, unless you have to move some furniture. Take down a ceiling fan over your head, or a mirror hanging behind the bed, or something like that. Okay, so there's another one that would be the second most likely one is the part of the San Andreas running right up the San Francisco Peninsula through San Francisco past the Golden Gate Bridge. I would anticipate, I would be surprised if one of those didn't move during this century. I didn't say it would, I just said I would be surprised if it didn't. Now, here's the last bit. Back to Southern California again, San Diego, Salton Sea. And if we do the San Andreas Fault, what I want to show you here, I'm going to try to emphasize, is what we geologists call the big bend in the fault. So if you visualize that this fault goes down about 12 miles deep, you can almost visualize this as like a 12-mile high wall. And then what do we have? We have part of Southern California we're on pushing against that fault, that bend. And what happens to the topography here? San Bernardino Mountains, Gorgonio Mountains, Santa Monica Mountains. Why are they there? They're there because, like the blue arrow shows, it's pushing against and raising up mountains. This is also big for earthquakes. And what I want to show you on this one is, if I take this spot here, take that San Andreas and say, here's this 12-mile high wall, and this side's pushing against it, it's not the other kind of fault like this. It's going to be what? It's pushing, and it's going to go. Which one's going to be worse for people? You're in your house. The ground goes like this, or the ground goes like that. We call those thrust faults. And what I want to show here then, my last two, we have this drawn. I love it as a piece of artwork, but it's pure science. So I had some very talented students do this. So this is 10 or 12 miles thick. That's a fault. The different colored sections are from the past earthquake records, the things we do by digging trenches. So here's the San Andreas. Here's Elsinore, Rose Canyon. But notice that area where the mountains were east-west, the transverse ranges. Here's what I want to show you then. These thrust faults. Right here, this is 1971 San Fernando earthquake, where the ground ruptured and moved south. Magnitude 6.6 earthquake, killed 67 people. You see all these lavender dots right here? Those are movements with the Northridge earthquake in 1994. This time, the fault ruptured, and it ruptured the other way. It's almost like a bulldozer pushing the landscape. Okay, so here we go. See this green? See this yellow? That's the same fault trend. So I'm going to go say 1971, 1994, this in your lifetime, that in your lifetime. My guesstimate. I don't know that, but that's, is that enough depth and destruction for you there? Those four. Okay. That's it. We're done. So I'm not moving from California. I like it here very much, but I do try to understand nature and live along with it as best as I can. So if you have any